Okay, here we are again. Let's do another problem from beam deflections by using the double integral method, and just as a refresher, remember this is the equation of the deformation curvature, and we explained that before. We explained it in class also, and this is just a review from mechanics of material, the moment curvature relationship. This is the moment curvature relationship. So we do the first integral of that, we get the slope, and if we get the second integral of that, then we wear the deflection. We have the deflection. So let's do another problem related with this one, and the problem that I want to solve now is this. This is a fixed support, and this is a beam. In that beam, the only thing that I'm going to have is a vertical load here of 60 kilonewton, but this is a roller, and at the same time I'm going to have a hinge here, an internal hinge. This distance, each one of them are 3 meters and 3 meters. Find the equations for the slope and the equations for the deflection at any point in this beam. Okay, how do we do this thing? Same thing. Remember, I explained you in a previous problem that we have to find the reactions. This is the first step that we do, and yes, it's important to find the reaction, which is, it shouldn't be any problem calculating that. And once we find the reactions, remember we have to find what I call points of interest or discontinuities. We have to find the discontinuities, and those discontinuities are wherever you have a concentrated load, wherever you have a concentrated moment, wherever a distributed load begins or wherever the distributed load ends, or wherever you have an internal hinge, wherever you have any change. Anything that is important in change of geometry, change in stiffness. So we have to determine those points. If the material is changing, I need to recognize that there is a change there, and I need to put it. Why? Because as the material is changing, then the E is changing. If the geometry is changing, then I is changing. If you have concentrated loads of moment, that's gonna probably, depending on what you have, is gonna affect your equations also. So you need to do that. If you have an internal hinge, like in this case, the slope is going to change because the hinge is going to make the slope to change at that point. So you need to know that. First of all, calculate the reactions. This is like this is the point ABC. Let's say A, B, C, D. A, B, C, and D here. This is going to be dy, and here I'm going to have AY. And my moment MA. Remember, we're supposed to have AX also, but AX is going to be 0 by doing summation of forces in X. And because I have a hinge here, if you want to know if this system is statically determinate or indeterminate, remember how to do it. You count the number of reactions. You have 3 here, plus 2 here, 5, plus 1 here is 6. So your number of reactions is 6. Your number of bodies are 2 because you have 1 and 2 bodies. And if you have R equal 3 times, this is N, number of bodies, 3 times N, then that's statically determinate, and that's what you have, 6 equal 3 times 2, 6. So this is statically determinate. How do you do that? You make a section here at the hinge, and you calculate dy. How do you do that? By doing summation of moments here, and then you have 60 multiplied by 3, 180 in this direction, and then dy multiplied by 6 in this other direction, divide 180 by 6, and dy is 30. I'm not going to do that because that's statics, that's basic statics, and you should know how to do that already. So this is 30 kilonewton here. This one here is also 30 kilonewton. And this moment is 30 times 3 is 90 kilonewton meter. So reactions are calculated. Establish what are those interest points. Well, you have a change here, definitely. You have a change here also, definitely. So you are defining 3 regions. These are the 3 regions that I have to work with. This region, I'm going to call it 1. This region, I'm going to call it 2. and this is going to be my third region, region 3, 3. Those are my 3 sections that I'm going to do. Let's start with the first one, this region here, and I'm going to use the right side of that section. So for 1, 1, I'm going to use the right side of that section, and what we have is this. This is 30 kilonewton, which is my reaction. I'm going to measure x1 in this direction, or x in this direction. And of course I'm going to have my internal force, my shear here, and my moment. I know, don't tell me, I know this has to be in the other direction for summation of forces, etc., 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 but this is the positive convention accepted, so I'm just putting it like that, and I'm not calculating V1 for anything, so don't start yelling at me. Okay, M1. If I do summation of moments at 1, and remember this is the point 1 for me, equals 0, then you have that negative M1 plus 30 times x equals 0, or M1 equals 30x. That's basically it. And it doesn't say anything about EI in this problem, but I didn't say it, but the problem says once again that EI is constant. So wherever I use my equations, remember the equation once again, I don't want to copy it once and again and again and again. This is my equation. If this is constant, I'm just going to take it out of the equation like that, put it outside, and every time that I calculate my slope, it's going to be EI times the slope. But the slope is going to be constant, and at the end, everything is going to be canceling out. But remember, sometimes this is not constant. So I'm going to pass it here. EI times the slope is going to be the integral of the moment plus 1 constant, and that's what we're going to do. So my first slope for, remember, this part, 1, 1. And this is going to be slope times EI is going to be the integral of that, and the integral of that plus C1 dx, and this is going to be EI times the slope is going to be 15x squared divided by nothing, because I already divided by 2, it was 30x squared divided by 2 plus C1. And if I do the integration of this again, then I get V, EI times V, and EI times V is going to be the integral of 15x squared plus C1 dx plus C2. And we have that EIV is going to be equal to, this is 3, pass it here, it's going to be 5x cubed plus C1x plus C2. There you go. In this case, I'm not going to wait until the end in order to see if I can calculate any of my boundary conditions. I'm going to start right now, and I'm going to see what can I do. What do you know about here? Do you know the slope at this point? No. By the way, in this problem, what I'm asked to do is not the slope at any point. I want to calculate the slope at D, slope at D, and I want to calculate also the deflection at C. That's what I want to calculate. Deflection here, slope here. So what do you know about this? Do you know anything? Can you infer anything about this point? Well, not about this one so far, but about this one I can. The slope, I don't know. That's what I'm asked to calculate. But definitely the deflection here has to be 0. And here means here. And here means x1 equals 0, because I started measuring my deflection from here. So for boundary conditions, I know that my deflection is going to be 0 when my x is going to be 0. So if I put my x0 here and I make this equal to 0, I have 5 times 0 plus C1 times 0 plus C2 equals 0. So C2 equals 0. There you go. I know this is going to be 0. And that's just going to be simplifying my equations every time that I start working. I got one of the constant already out of my system. I don't know the slope. And remember, I still have some equations that I can use. Now let's go to the second part at 2-2. My section 2-2. My section 2-2 is here. I could use right, I could use left. I'm going to use the same side, this side, because I think it's a little bit easier or straightforward to do. So this is going to be 30 kilonewton. This is pretty much the method of the sections that we learn in statics, guys. This is X, and now I put my balance forces, my internal forces, V and M. And if I do summation of moments at 2, remember I'm always calling this point 2. So I'm going to do summation of moments at 2 equals 0. If I do moment here, you get this moment, negative moment because it's coming in this direction. 60 times this distance is going to be negative, and this distance is x minus 3 times 60 plus this force times x plus this direction plus 30x equals 0. This is going to be negative 60 plus 30. This moment passes to the other side. That means that I'm going to have a negative 30 here and a positive 180. Moment is going to be equal to negative 30x plus 180. That's my moment for 2-2. Now what do you do here for 2-2? For 2-2, I'm going to do the integration of this. Remember, the integration of the moment. Integration of the moment is going to give me the slope multiplied by EI. So EI times the slope, or if you want to copy it, more professionally, that will be EI multiplied by dV at dx, aka slope. That's going to be equal to the integral of this plus one constant. Now, I named before my constants C1 and C2. Do not fall into the temptation of calling them the same, because they are not. So for this case, it's going to be C3. This is one of the things that I didn't tell you, but for every section that you do, you're going to have two unknowns, two constants. So C1, C2, C3, C4, C5, C6. So you need several boundary conditions in order to calculate those. Okay, plus C3. Do that. EI times the slope is going to be, this is going to be negative 15 x squared plus 180 x plus C3. And if I do the integration of this again, I'm going to get my V, my deflection, just by integrating that. So if I do that integration, I'm going to get EIV. It's going to be, I integrate this is going to be 3, positive dividing here, negative 5x to the third, 180x divided by 2, 11 squared, so plus 90x squared, plus C3x, plus my new boundary condition C4. There you go. What can I get about this here? Remember, very important this, very important. Even though I call this x, this equation isn't going to work for this part, because this part is kind of fixed here. So this equation works between 3 and 6. Between 3 and 6. Between 3 and 6. That's when this equation is reliable. Between 3 and 6 meters. Measure from that side. So basically I can't get anything so far. The only thing that I could get, if you think a little bit, is what happened at this boundary. We did this section and we did this section. This section goes from 0 to 3, measured in this way, and this other section goes from 3 to 6, because this part is basically not working, so my x has to be from 3 to 6. But at this point, when x equals 3, you are in this boundary. What happened at this boundary? Well, at this boundary, the deflection of this should be something like this and here is going to change in this part, and it's going to continue your deflection up to that point. But if you look at this point here, what happened here is that my slope is measured in this way for both cases, so my slope is going to be the same, and my deflection is going to be the same also at that point. So I can start by working first with my slope. My slope is going to be exactly the same for this point and this point, as well as my deflection. Let's start with the slope. So if I say that the slope for 1, 1 at x equal 3, look, my slope 1, 1 at this section at x equal 3, because I'm measuring x in this way, has to be equal to my slope 2, 2 at x equal 3. Then let's put those equations. This EI and this EI for my two slopes. Where's the other equation? Here. I didn't frame it, that's why. This one. Okay? This is my equation. So EI slope, this EI is going to cancel this other EI. So what I get from there is that this 15 x squared plus c1 is going to be equal to this value, negative 15x squared plus 180x plus c3. There you go. Once again, this value is the slope that I calculated for my section 2, 2, evaluated at 3, because I'm going to evaluate it at 3 now, and this other one is the slope that I got from my section 1, 1, and I'm going to evaluate it at 3 because it's the same point. So once you do that, you put 15 times 3 squared plus c1 equal negative 15 times 3 squared plus 180 times 3 plus c3. Pass this c3 to this side, c1 minus c3 is going to be equal to, when you solve this, you get 270. And I'm going to call this equation 1. Now, the other thing that you know about these 2 points is at that level, the deflection is the same also. So I'm going to make use of that for my boundary conditions. The deflection of my section 1, 1 for x equal 3 is going to be equal to the deflection of my section 2, 2 at x equal 3. What is my deflection here? Well, my deflection is 5 x to the third plus c1x. And remember, we calculated this as 0, so I don't going to put it anymore. And that has to be equal to my deflection that we calculated in 2, 2, which is this one. And this one is negative 5x to the third plus 90x squared plus c3x plus c4. There you go. Now, x equal 3, x equal 3. 5 times 3 to the third plus c1 times 3 equal negative 5 times 3 to the third plus 93 squared plus c3 times 3 plus c4. 3c1, pass this to the other side, negative 3c3 plus c4 equals, when I solve this, that's going to give me in this side 540. And I'm going to call this equation 2. Now compare this with this. So easy. I have 3 unknowns, 2 equations. Can I solve it? Yes. What? 3 equations, 2 unknowns. How are you going to solve that? Well, because this is C1, C3, and this is 3C1, 3C3. So what if I get this value, and I multiply this value by negative 3, and I add them up? So if I multiply this by negative 3, multiply 1 times negative 3, and I put it here, So I have negative 3c1 plus 3c3 has to be equal to 3 times this, which is negative 810. Add both equations, this and this cancel out, this and this cancel out, and I get that C4 equal 270. There you go. This is one example of how can you solve a system of three equations with two equations with three unknowns. Not really. What happened is these two are linear dependent one to the other. So one equation was included in the other one. But I got C4, which is the one that I was looking for. So we have already another of our constants. Now let's keep working. Don't lose perspective. Still I need to get my other constant in order to do that, in order to solve my problem. So I have to do necessarily this section here at 3 because I'm still missing C1 and C3. So I'm going to make this section here at 3 and I'm going to select, of course, this side because it's the easiest one. So for 3, 3, I'm going to do that. This is going to be my reaction, 30, my moment, 90. This is going to be my beam. And at this end, of course, I'm going to have V and M. Remember that these are the positive convention for this side of the beam. When we were using the other side of the beam, the other side of the beam, my shear was up and my moment was in this way. Now I'm selecting this side, my shear goes down, my moment goes in that way. This is the positive accepted convention. And my X is going to be measured from here to there. There you go. Okay. Now we do summation of moments at 3 equals 0. Remember, I'm calling 3 always the end of my section. So if I do moment here at this point, then we have positive 90, positive M, minus 30x equals 0. So my moment is going to be 30x minus 90. What do we do now? Well, what we do now is that we do the integration because, remember, once again, if I want to calculate my slope, I integrate the moment. If I want to calculate my shear, I integrate not my shear, my deflection. I integrate my slope. So let's do that. I multiplied by my slope is going to be the integral of this 30x minus 90 dx plus C1, C2, C3, C4, C5. That's my new constant, C5. So this is EI, my slope for 3, 3 is going to be 15 x squared minus 90x plus C5. And my shear is going to be the integral of this. So EI, oh my god, not shear, deflection. EI, deflection, is going to be the integral of this. Plus C6. Or EI, deflection, yay, I say it correctly, is going to be equal to, this is going to be 3, so 5x to the third minus 45x squared plus C5x plus C6. What do we know about here? Can we know something about that help me out finding boundary conditions? You know, luckily, yes. Fortunately, yes, we can. Because if you look at this again, this is a fixed support. That means that at this point, my deflection is going to be 0, but also my slope is going to be 0 because it's a fixed support. I love fixed supports because of that. So deflection 0. And slope is 0 here also. What does that say? Is that if I put x here in my first equation, EI zeta equal 15 times 0 squared minus 90 times 0. plus C5, that has to be 0. That means that C5 is 0. Nice boundary condition, nice constant. Now, for the deflection, EIV equal what? 5 times 0 to the third, whatever, minus 45 times 0 squared, plus C5, which is 0, times 0, which is 0, plus C6 equals 0, C6 equals 0 also. Yes, nice. Okay, but how come we calculated everything and we can't say anything yet? Because we haven't calculated everything. Let's go back to whatever we calculated before. We calculated C4, but we don't know C1, we don't know C3, and sadly we need C1 and C3 for calculating what we're looking for. C1 for the deflection here, and C3 for the slope over there also. So I can't do anything if I don't have C1. C3, I don't care too much. I could live without C3, but definitely C1 I need it. The only way that I can get C1 is calculating C3. Now, what else do we know about this? What else can we do? Oh, look, there is a relation that we haven't used yet, which is this one. Look, the slope here, because this is a hinge, changes. If I'm studying any point here, for example, here, the slope in this side and the slope in this side is going to be the same, because it's the same point, and because it's the same beam. But because I have this slope, this hinge, the slope here is going to change due to the hinge. So I can't compare this slope with this slope. But definitely the deflection for this part and the deflection for this part has to be the same. Now pay attention, because this is a tricky part. When we calculated the deflection here, we call it EIV here for 3,3. For 3,3, deflection has to be equal to the deflection for 2,2. Deflection for 3,3 at this point has to be equal to the deflection for 2,2 at this point. But look at this, because this is another thing that people get messed up. The distance x for this one is how much? 3. But the distance x for this one is 6. So be very careful with that. Now let's put this equation first, the equation 3,3 that I already set up here. Equation 3,3, and we have it basically here, is 5x to the third plus c1x, right? 5x to the third plus where are you? Here, 5x to the third. Remember, this is 0, this is 0, so 5x to the third minus, not plus, minus 45x squared. But remember, this x is going to be 3, and this has to be equal to my slope from 2, 2. Where is my slope from 2, 2? Nobody moves. My slope from 2, 2. Here is my slope from 2, 2. This one here. So my slope from 2, 2 is negative 5x to the third plus 90x squared plus c3x plus c4. Just remember that we just calculated c4 before. That rhymes. C4 before, and it was 270. So that value here is going to be 270. But this x has to be how much? How much? 6. Because I'm starting from this point to this end. 6. Now put everything together. 5 times 3 to the third minus 45 times 3 squared equal negative 5 times 6 to the third plus 90 times 6 squared plus C3 times 6 plus 270. And when you solve for C3, you get negative 450. And we're done, basically. Just 5 more seconds. Not seconds. A little bit more. Now, if you remember this equation that we set up before here, when we set up that this equal to this, and we say, let me name that equation, equation number 1. By the way, that's the only equation that I named. I know I named these two also. But equation number 1. So, from 1, equation 1, we got that C1 minus C3 equal 270. If I put this C3 now here, then you have that C1 minus what, 450 equal 270. That means that if I pass this to the other side, C1 is going to be equal to negative 180. Now we can go and calculate what we are asked to do after I don't know how many pages of working and working and working. Let's go back to our original page, which is this one. Calculate a slope at D and deflection at C. Oh, look at that. The slope at D, I can calculate it here for x equal 1. And deflection at C, no, the slope at D is here for x equals 0. And deflection at C is the same equation here for x equal 3. So let's use this equation for a slope first. My equation for a slope is EI slope equal 15x squared plus C1, but C1 is, we just calculated negative 180. That means that my slope is going to be, and remember I have to evaluate that at 0 because they are asking me for my slope at D. So my slope at 0 is going to be equal to 15 times 0 squared minus 180 divided by this EI, in case I don't need it now, and my slope at 0 is going to be negative 180 divided by EI. Important again. Remember, this slope is showing negative only for the reason that I'm analyzing my x measured from this end to this side. So if I'm gonna refer to my slope as negative, it's because I'm referring to my slope in this direction. Once again, this is my beam, this is my roller, this is the hinge, this is the deformed shape or something like that. This is showing negative because I am using x in this direction. If I want to express my slope from this other way, let's say this is from D to C. If I wanted to express my slope from C to D, my slope from C to D at the point D, remember, it's going to go in this direction and it will be positive. Remember, in this way it will be positive, in this way it will be negative. So be very clear, be perfectly clear when you express your values of your slope. Deflection is easier because deflection is negative, positive. There's not too much to say about it. Which brings us to the deflection also. Deflection is this one. So my equation is EI times V is going to be equal to 5x to the third plus C1 times x. And C1 is 1. So my deflection is 5 times. Deflection where? Deflection at C. Remember, I'm measuring from this point to this side. So this is 3 meters from here to here. X equals 3. So 5 times 3 to the third plus C1, but C1 is negative 180 times x, and x is 3. So my deflection is equal to this pass divided here, EI, negative 405 divided by EI. Of course, the units of deflection will be theoretically meters, because I'm working everything in meters, if these units are coherent with that unit. So negative 405 EI. Why negative 405 EI? Because negative, what it means is a deflection downward. Negative 405 divided by EI. Finally, summary, slope, depending if I'm measuring DC or CD. If I'm measuring slope CD in this direction, it's going to be positive 180 divided by EI at the point D, and deflection at the point C is going to be negative 405 divided by EI. If I want the slope here, the deflection here, what do I do? Well, I put that in the corresponding equation. If I want my slope here, what do I do? Oh, slope here is going to be different than this slope. You should do that, okay? You should calculate the slope at this end and the slope at this end, so you realize the difference in the slope between this point, and you figure it out, okay? Well, this is the other problem that I have for double integral for calculating beams. I hope that you enjoyed, at least you understood it. Most important thing, remember, you use double deflections because you use the moment curvature relationship that you learn in mechanics of material, which is this one. If you do the first integral, you get this slope plus 1 constant. If you do the second integral of the slope, then you get the deflection with the second constant. How do you get the constant? By applying boundary conditions and finding each one of them. And with that, you get your equation. See you next video lecture, guys. Have a good day.